It's hard to have patience, waiting on parts to arrive. Do I really need to wait when I do have a fairly well-made bobbin? I think I'll give it a try, at least get an idea of the power output. I'm going to start with the 12.3 volt secondary for the first winding. I have 2 strands of 30 gauge wire. I could probably get away with one, but I want to see how much copper I can get on this bobbin. One thing I have to do is make a much better holder for the bobbin. Holding it in an alligator clip, not really cutting it. I'm only doing 12 turns. I'll see how the voltages come out on the lower voltage rails. This is a flexible CA glue, and it really seems to be doing a good job on holding the windings in place. I am soaking up any large puddles of it. I'm going to need that space for wire. Now this is going to be the primary winding, so I'll start it on opposite sides from the secondary windings. I've let the glue on the previous winding harden for a little over 10 minutes. It's not that I need the previous winding held tight before I put this one on. I primarily want a good soaking in of the glue where the wires enter and leave the bobbin. But if the glue's not completely dry, you end up with it on your fingers, then all of a sudden your fingers are part of the bobbin. I'm going to do 21 turns for this winding, so this transformer will have a primary to major secondary turns ratio of 21 to 12, compared to my initial transformer of 22 to 13. That will lower the inductance by 3 or 4 microhenry, as I'm going to keep the same 0.4 millimeter gap. The 22 to 13 ratio transformer with a 220k ohm feedback resistor gave me an output voltage of almost 12.7 volts. I expect the 21 to 12 ratio to give me a lower voltage on the 12.3 volt line. But now the voltages will be higher on the 4-turn and 2 6-turn windings, and that's one reason to try with this turns ratio, to actually measure what secondary voltages I get. For this primary winding, I'm using 2 strands of 30 gauge wire. I'm trying to keep them close together. I'm not even sure if that's a good thing to shoot for or not.
19.
It looks like I'm going to have plenty of room on the bobbin for all the windings. There isn't much wire left to go on it.
21.
I'll coat with CA glue and let it dry. This is the 3.7 volt secondary. So I'm doing 4 turns of a single 30 gauge magnet wire. I'm still cutting the wire for this winding way too long. No glue after this one, going to go right to the next winding. For the last winding, I'm using 2 strands of 34 gauge wire. I'm going to wind 6 turns, then break out for a center tap, then wind 6 more turns. The center tap will help me keep track of the polarity of this winding. Short wires go to the negative rectifier, center tap goes to ground, and long wires go to the positive rectifier. I'll coat it well with a bit of glue. Nice the way those 34 gauge wires drop into the 30 gauge crevices.
4, 5, 6.
I'll carefully remove the layers of tape holding the leads. All the long leads represent the same polarity for each winding. I need to work on a way to label them. I could save a bit of wire that way. I'm using the same core gap as before, a close to 0.2 millimeter thick sheet of plastic glued to 1/2 of the core, giving me a total core gap of about 0.4 millimeters. The hot glue is working pretty good holding the core halves together, but it makes it impossible to try and change gaps with the transformer mounted. Maybe not impossible, but I need to make a mounting bracket for the core, because I do want to see what kind of effect altering the gap has. That's a lot of wires. I'm really glad I installed the pins on the PC board. Being able to wrap the wires around the pin is much easier than trying to hold 2 wires in place on a solder pad. I can see now why they don't offer an 8-terminal carrier for this core. They don't expect someone to try and run that many wires out of it, and for good reason. Well, the 12.3 volt output is 12.1 volts, a bit lower than I was expecting, but I now have a load on all three of the other rails, and quite a bit more load on the 12.3 volt rail. I have about 50 milliamp load on both the plus and minus 5.7 volts, and about 130 milliamps on the 3.7 volt line. All these voltages are taken with about a 280 milliamp load on the 12.3 volt line, so probably absolute maximum that line would ever pull. .7 volts is okay, 3.75 volts is okay as well. Both of those voltages are at the upper end of what I would like, the consequences of the 12-turn major secondary winding. Even with the 12.1 volts pushing 350 milliamps, it's regulating pretty good. Now at the extreme, about 460 milliamps load on the 12.1 volt line. The 6-turn lines are now up to their respected 5.9 volts. And the 4-turn line is now up to 3.85 volts. But I believe those would be the maximum voltages on those lines. Well, the 12.1 volts might move higher. I'm at over 6.5 watts output power, most of it in the 12.1 volt rail. This is the primary waveform at the 6.5 watts. Oh, I did put a 30 ohm 220 picofarad capacitor in as a snubber on the primary to dampen that very high frequency ringing, and it looks to have done a pretty good job of it. Can see that even at 6.5 watts, I'm still well within discontinuous conduction mode. And at a more of what I would expect as normal operating power level, about 4 watts, can see I'm only at about 30% duty cycle. You know, I think Maxim were being very conservative with the 7.5 watt rating. I do think with this turns ratio, my 12.3 volt line will have to run a bit low. The lower voltage secondaries are about at their upper limits. Of course, all the extra voltage above what the LDOs require will be dissipated as heat, so I'd like to keep that down as much as possible. Also, the fact that the low noise 5 volt regulator I intend to use has a maximum input voltage of 6 volts, getting quite close to that, particularly if something were to short out and put a heavy load on the 12.3 volt rail. But if my secondary turns are 12, 6, 6, and 4, a divide by 2 might possibly be worth a try. While I'm still waiting for the TDK bobbins to come, I thought I would make some labels for the transformer leads. So I printed some letters and numbers on some 30-pound paper, cut them into tiny strips. Everything tiny is so difficult to work with. I put a bit of yellow wood glue. It's all I had on hand that works really well with paper. Then tape the strips to the shaft of a small screwdriver. Wrap it around the shaft, hold it for a few seconds, then move to the next one. Once the glue sets a few minutes, then I can push the now formed labels off the shaft. It's easier if I don't overdo the tape holding it to the shaft. I think those are going to work just fine. The TDK bobbins made for this core have arrived. Should give me a bit more wire winding area. Also, the notches on these bobbins go all the way to the center winding area. I didn't cut mine that deep, and I should have. Another improvement is my bobbin holding setup. A small chuck held in a vise, and there's enough weight there that it won't be moving around on me a whole lot. The inside diameter is a bit larger on this bobbin, so it slides on the holding spacers quite easily. Yeah, that is too loose. It will move around way too much on me. I'll put a tiny bit of CA glue on it, not the flexible stuff, just the regular brittle CA glue. Should break loose just fine. I'm going to start by cutting the lengths of wire I need. I'm going to cut 2 pieces of 30 gauge, 25 inches in length. This is for the primary winding. The 12.3 volt secondary gets two 15-inch pieces of 30 gauge. Then I'll cut two pieces 7 inches long of 30 gauge for the 3.7 volt secondary. I'm knocking over 4 inches off of the length of these compared to the last transformer. And then one 30 gauge 9-inch piece for the 5.5 volt secondary. And lastly, two 9-inch pieces of 34 gauge for the minus 5.5 volt secondary. So really just a minor change from the previous transformer I made. After letting the glue set on the bobbin for a few minutes, I'm going to start with the 12-turn secondary. It's hard to tell from the video, but the TDK bobbin looks to have a bit more area for winding than my homemade ones did. The plastic is thinner, so that should give me a bit more space. But the perception of more space may be greater than the actual increase in winding area. This winding has the same turns and position in the transformer as the last one. I think I can reduce the length of the wires for this winding a bit, as long as it stays as the first winding. Then I'll put a bit of CA flexible glue on to hold the winding in place, soaking up any puddles. Then I'll put my V1 wire label on. I'll put the labels on the ends of all the wires that are to attach to the rectifiers. I'm going to do this the same as the last primary. 21 turns with two strands of 30 gauge wire, and in the same position as the last one. Started and ended opposite the secondary side of the bobbin. Still trying to keep the wires right next to one another, only somewhat successful at it. I think this is about the right length for this wire, one wrap around the spacer with enough room left for me to put the label on. I think the little temporary wire labels are going to work great. I do have to make sure they can't fall off the end of the wire. Put on some glue. Wipe off the excess. I'll let it harden for a few minutes before I start the last of the windings. The next windings are where the differences between this transformer and the previous transformer are. The first difference is this winding now gets two strands of 30 gauge wire instead of one, still at 4 turns. I can tell there is a noticeable increase in winding space with this bobbin, so I'm glad I ordered them. I overdid the shortening of these wires, I see. Another half to 1 inch would have been perfect, but it will do. With the wire labels, it looks much more tidy, and I like that. No glue after this one. We'll go right to the next winding. Now I'm going to go with 6 turns of one strand of 30 gauge wire, and this is for the positive 5 volt rail. The one strand of 30 gauge will give me a bit more wire area than the 2 strands of 34 gauge, just in case I need a little more current out of the 5 volt rail. I really need another inch on the length of these. I'll have to remember to add about 10% in length for the outer windings. No sense in making it difficult to work with. Still no glue after this one. Going to go ahead and put the last winding on. I'll put the label on the start of the wire, as this will be the end that connects to the minus 5 volt rectifier. This is still 2 strands of 34 gauge with 6 turns, like the last transformer, but this is not part of a center tapped winding. Trying to keep the 2 strands together, but they fall in between the 30 gauge wires. Of course, this wire is a bit on the short side too. I'll put plenty of the flexible CA glue all around the winding, soaking up the extra, mainly to make it easier to tear the winding apart later. After letting the glue dry for about 15 minutes, I can start freeing the wire leads. The 30 gauge leads are pretty tough, but I do have to be a bit careful removing the tape that holds the 34 gauge wire. I've cleaned all the glue residue off of the core half. Think I have a better way to gap and measure the gap. Instead of measuring the thickness of the gap material, I measure the core width with the 2 halves together at 0 gap. I'll keep track of the 8.356 millimeters, but the micrometer has a button for that. Also, I'm going to use multiple layers of Kapton tape for the gap spacer. I think the Kapton tape will be more stable than the plastic I was using. If it was Mylar, then maybe not. I don't even know what kind of plastic that sheet was made of. At least I know what material I'm using with the Kapton tape. I'm going to try 4 layers. The tape seems to measure about 0.06 millimeters, so 4 should give me a bit more than the plastic sheet. The plastic sheet and glue end up measuring right at 0.19 millimeters, so inductance was a little more than I calculated. Four layers is pretty hard to cut through. I might want to put on 2 layers, cut that out, then do 2 more. Bit of trimming so the bobbin will fit easy. I don't want the tape pulled off the edge of the core. It's really quite thin on the outside rim. I'll put a bit of pressure, trying to mash the tape flat. Now to measure what size of gap I get. That's not far from the 0.06 per layer. So I've got a gap in each leg of 0.232 millimeters. So my inductance with 21 turns and a gap of 0.38 millimeters calculated to 40.5 microhenries. Now with the 0.464 millimeter gap, I'm at 33.4 microhenries, which is still well above the 26 microhenry minimum I need for the transformer. One more layer of tape and that would put me very close to the minimum inductance, closer than 10%, so I'm not going to try that at this time. Along with ordering the bobbins, I also ordered some tantalum polymer SMD capacitors. I was pushing almost a volt of 120 kHz ripple on the 12.3 volt line. I'm not sure how much that was messing up my voltage reading, or possibly the controller's voltage sampling. So I've replaced the radioelectrolytic capacitors with the polymers. I end up putting a 22 microfarad on the 12.3 volt line, 47 microfarad on the 3.7 and 5.5 volt lines, and a 10 microfarad on the negative 5.5 line. I also made an acetal holder for the core. That should let me change the gap without removing the transformer windings from the PC board, as long as I remember to install the proper side of the core first. I'll make sure it all fits before I solder the leads on. I'll still use the hot melt glue to hold the core halves together. It turns out the glue pulls off the cores quite easy, and I'm pretty sure it shrinks a bit on cooling, so that should put a bit of pressure on the core. And of course, the glue will hardly stick to acetal. I'll set it up for a few tests, see where I'm at. I've got the input voltage at 20.5 volts, 11.95 volts, even lower than the last transformer. 5.72, that's about the same. 3.75, that's also about the same. All these readings are at about a 200 milliamp load on the 12.3 volt line, about 50 milliamps on the plus and minus 5 volt lines, and 140 milliamps on the 3.7 volt line. The primary switch line I think looks pretty good. Again, running at about a 30% duty cycle with a 3.5 watt load. Channel 2 is the 12.3 volt line ripple voltage, a little over 100 millivolts, much better with the SMD capacitor. This ringing at the start of the charge time, I don't know if that's because the snubber I have on the rectifier is really bad values. Maybe it's the way I'm measuring it is the problem. It's around 2 megahertz of ringing right across a 2.2 microfarad SMD ceramic cap and a 22 microfarad SMD polymer cap. This I also find a bit strange. I would expect the rectifier would be reverse biased at this point. Is this from the capacitance of the Schottky diode and the snubber on it? A quick look at the ripple on the 3.7 volt line. Some of the same issues, plus these two slopes are different. This one I would expect to be the resistance load on the line. But why is this one during the capacitor charge period steeper? And really, why is it not sloping upwards? I've got a lot of questions. Hopefully there will be time to dig into the answers. I do want to compare the voltages to the first transformer, so I've got all the loads about the same. Main thing is the 12 volt line has around a 280 milliamp load on it. 11.96 volts. Controller does do a good job of regulation. .8 volts. .78 volts. So my 12 volt line is lower and the lower voltage lines are a tiny bit higher. Not the direction I want to move in. I do want to check the temperature rise of the transformer. This one feels cooler to the touch than the last one. There is a bit of air moving in the room, so it will read a bit lower than what the still air reading would be. I've got about a 6.7 watt load on it, so about maximum for what the design was. Around a 7 degrees centigrade rise. That's not bad. The controller feels cooler than the transformer. It feels like the output rectifier may be the warmest part. It all looks great, except I would like to have more voltage on the 12 volt line and less on the three others. More winding to do. For this transformer, I'm going to do 22 turns for the primary, 13 turns for the 12.3 volt secondary, 4 turns for the 3.7 volt secondary. All of these will use 2 strands of 30 gauge wire. Then I will do 2 windings of 6 turns each for the positive and negative 5.5 volts. Each of these will be with a single strand of 30 gauge wire. I'm going to remove these windings, see if I can keep the leads labeled as I unsolder them. The hot melt glue is working great for this. Enough adhesion to hold the core tight for testing, but it's very easy to remove and doesn't damage anything. The core holder, along with the glue, makes it easy to take the transformer apart right on the PC board. I've got a label on all the leads that need one. Question is, can I hang on to it a bit and not knock a label off? I'm going to try. This was one of my most efficient cores, not sure why. It did probably have the most copper in it, but this next one will have even more. I have all the winding leads sorted and the core in place, and everything hooked up to test. 12.4 volts on the 12.3 volt line. -3.6 on the 3.7 volt line. -5.5 on the -5.5 volt line. Wow, 4.5 on the 5-point line. I missed a turn. I should know better. Can't talk to people and wind a transformer at the same time. But I can still use this to test. That one winding missing a turn is not going to affect the reflected voltage to the primary that much. These voltages are all with about a 200 milliamp load on the 12.3 volt rail. Of course, the 5.5 volt line will now have around 40 milliamp draw instead of around 50, but still looking at a total power output of around 3.5 watts. The voltages are just what I'm looking for, well, except for the missing turn on the 5.5 volt winding. I'll just ignore that for now. Now I'm going to move up to 4.5 watts of output. 12.4 volts at 280 milliamps, 20 millivolts lower than at 200 milliamps. -3.62 volts, -5.5 volts, and 4.56 volts. If I pretend the 4.56 is really 5.5, then these are just the voltages I'm looking for. Input is approximately 5 watts and output 4.5 watts. About 90% efficient. Not bad considering I'm not quite sure what I'm doing here. Might as well test the extreme. 12.5 volts at 480 milliamps. A little over 7 watts of total output. The lower voltage secondaries are 3.7 and 5.65, well below my upper limits. This is the primary switch waveform at 20.5 volts input. There is still a bit of float time on the transformer. My on switch time is 4.24 microseconds out of an 8.1 microsecond period, at a little over 52% duty cycle, nowhere close to the 65% maximum. But at this load and input voltage, the transformer is only off for about 240 nanoseconds. Have to be getting very close to boundary conduction mode. I'll start lowering the input voltage and see how the regulation goes. Still regulating quite well. This is at 19 volts input, and I'm pretty sure have reached boundary conduction mode here. I guess I would need a current probe to tell for sure. On time is around 54%. Well, I'll take it down some more. Okay, now down to 16.2 volts. It's still regulating very well, and at about 59% on time. Now at 16 volts input. It is now unstable. Even though the output voltage is still regulating, I would not want to run it at any lower input voltage. Of course, if it normally runs at about 4.5 watts, it will easily run with a 16 volt input. I'll start raising the input voltage and see how regulation does. about an 80 millivolt change from 16 to 25 volts. Up and down along the way. That's better than a 1% change in output voltage over the input range. The more I play with this Max 17691, the more impressed I am with it. I guess it would be a good idea to test at the opposite end of the power range and see what happens. I have a 13 volt Zener in series with a small diode on the output of the 12.3 volt line. The datasheet warns that a Zener diode should be placed on the output in the event the minimum load cannot be met. Well, going to test that. Only there will still be a load on the lower voltage secondaries. So the 12.3 volt line clamps to the Zener voltage, about 13.8. .48 on the 3.7 line. That will do, maybe a bit low. .3 on the 5.5 line. That will work for the positive, but is a bit low for the negative regulator. Also, it has started switching back and forth between 120 kHz and 30 kHz switching frequency. So I'm below the minimum output load for continuous 120 kHz operation. I would say about 20% of the time it's operating at 30 kHz. As I reduce the load, it will move to continuous 30 kHz operation, and then down to 7.5 kHz operation. Here, the only thing on the output lines are the Zener diodes. It is operating continuously at 7.5 kHz, and the input power to the entire power supply is like 2 milliamps. I think I'm going to go with this transformer layout. There will be no trying a divide by 2 on the winding turns. The 22, 13, 4, 6, and 6 seems to be just about right. I may try one with 21 turns for the primary just to see what difference it makes. The previous transformer ran a bit cooler, so more efficient. But this operates over the input voltage range I need, and if I can get around 90% efficiency, that's more than I was expecting. Next episode, the actual power supply, I think. Thank you for watching.